Hello everyone, this is Preetu Ghosh, a master's student at Sirindhorn International Thai German Graduate School of Engineering, or TGGS. This presentation is a part of my course Broadband Wireless Communication Systems under the guidance of Associate Professor Dr. Chanyo Pirak. Today I will present on spectrum sharing strategies for secure and efficient 6G network based on a study of key research papers. For this project, I reviewed three main papers. Each paper focuses on different aspects of spectrum sharing. First, the algorithm that helps maximize spectrum usage. Second, how we can make spectrum sharing more secure and distributed. And third, how adaptive techniques using AI can help future 6G networks become smarter and more efficient. So, why spectrum sharing? 6G will connect billions of devices, all needing fast, reliable data. But radio spectrum is limited, like traffic lanes that can get crowded. Without sharing, many users would face delays and poor service. Spectrum sharing improves efficiency by allowing different users and networks to access the same frequency bands. AI-based methods also make it possible to prioritize important users like hospitals during emergencies and ensuring fairness and faster service. This is a comparison of 6G with existing 5G over various parameters. 6G network will bring major improvements compared to 5G, not only if spectrum is managed properly. They will feature extremely low latency, very high data rates, and dense device connectivity. By introducing smarter sharing strategies, 6G can achieve these targets, providing faster, more reliable, and safer wireless communication for future applications like smart cities, remote surgery, and self-driving cars. When we compare 6G and 5G, the difference is clear. 6G target latency under 1 millisecond, while 5G aims for 10 milliseconds. 6G will deliver peak data rates up to 100 Gbps, supports millions of devices per square kilometers, and offer almost 100% reliability. Also, 6G will use spectrum resources much more efficiently, 3 to 5 times better than 5G, which makes spectrum sharing even more critical. In the first paper, researchers explored different spectrum sharing algorithms, SSAs. The main goal of this algorithm is to maximize the usage of available spectrum while minimizing interference between different networks and users. SSAs enable dynamic access to underutilized frequency bands, making sure no part of the spectrum is wasted. The key contributions of SSAs include efficient handling of data packets, improved user privacy, and better coordination between networks. With this algorithm, networks can smoothly transition users between different frequency bands depending on demand, ensuring better service quality without interruptions. This figure shows the basic flow of adaptive spectrum sharing. The system constantly monitors the environment, detects free spectrum opportunities, evaluates user demands, and dynamically assigns the best available resources to each device. It works like a smart traffic controller that adjusts traffic flow to avoid jams and improve travel times. It shows full hardware and software pipeline that receives a signal via antenna and process it through digital and analog converters. Then assigns it a proper channel, corrects it and secures it, and finally routes it to the user, all while enabling spectrum sharing through smart processing. The second paper points out a big problem. Today's spectrum sharing often depends on centralized databases, which can be attacked or fail. The paper proposes a distributed AI based system where each network uses its own local observation without relying on single control center, making it more secure and scalable for future networks. The experimental evolution here in a network of three base stations, they tested their distributed method. The results show that their approach converges faster and achieves much higher throughput compared to traditional WMMSE and random methods. This means the network becomes more efficient and can serve more users with better quality. Here, WMMSE is a centralized algorithm used for power control and resource allocation. In the three base station network, the proposed method quickly learns and outperforms both WMMSE and random allocation, and achieves the highest throughput. Even when the network complexity was increased to seven base stations, here seven base stations, the distributed method continued to perform very closely to the centralized optimal solution. This proves that their system scales well and can handle more crowded real world scenarios without losing efficiency. The third paper focuses on how adaptive spectrum sharing will be critical for managing the explosive growth in wireless data traffic in 6G. By making spectrum use smarter and more flexible, we can meet the demands of emerging applications like real time video, AR or VR, and industrial IoT. The main strategies they propose are AI based decision making to dynamically pick the best frequency, dynamic interference management DIM to avoid signal clashes, and cognitive radio technologies that can sense available spectrum in real time and make fast adjustments. These strategies together create a highly responsive and efficient communication system. This working model shows how an adaptive spectrum sharing system operates. It starts with environmental sensing, applies all AI algorithms to decide the best spectrum allocations, and constantly adjust based on real time network conditions, maintaining the best possible user experience. In conclusion, the spectrum sharing will be a backbone for 6G networks. Distributed AI driven sharing will improve spectrum efficiency, reduce latency, enhance network reliability, and support future advanced features like joint communication and sensing, GCAS, JCAS, and sub-THz communications. Without smart sharing, 6G's potential would be limited. Here are the papers and research works that form the basis of the presentation. They provide detailed models, simulations, results, and future directions for spectrum sharing in 6G network. This brings me to the end of my presentation. Through studying different spectrum sharing strategies, we can see that smart, adaptive, and secure spectrum management will be essential for making 6G networks truly efficient. This work was part of my Broadband Wireless Communication System course at TGGS, and I would like to sincerely thank Associate Professor Dr. Chayat Pirak for his guidance. Thank you very much for your attention. If you have any questions, I would happy to answer. Thank you.